In this lesson, we'll take a look at what logarithmic functions are. And right at the top here, we have x equals a to the power of y. That's called an exponential form. It's called exponential form because it has an exponent, which is in this power. A to the y is a power, and so that's called an exponential form. The equivalent logarithmic form, so for any exponential form, there's an equivalent logarithmic form, and we'll often convert back and forth between one or the other. And what the logarithmic form does, and one of the things that logs were originally invented for, is to solve for an exponent. And so it changes the exponential form into a form that no longer has a power in it. And so the logarithmic form looks like this. The exponent y is equal to the logarithm of x base a. This is called the base of the logarithm, and it's the same as the number that's in the base of the power. Now, another way to write this in terms of numbers, bases, exponents, we could write the exponential form as this. Some base raised to some exponent gives some particular number. Well, the equivalent log form is the exponent. We're always solving for the exponent. So the exponent equals the logarithm, and it's the logarithm of whatever this base is of this number. Now, think of it this way. And I'm going to use some arrows here. If you're converting from the log form to the exponential form, so let's say you're given this one over here, and we're to convert into the exponential form. If you take this base and raise it to that exponent, it always equals that number. And so that's exactly what you have over here. Okay, so this base raised to that exponent is equal to that number. So that's how you convert from log form to exponential form. And that's what a logarithm means. It really means what power do I raise this base to get this number. And so in this table in the bottom here, we're asked to convert from either exponential form to logarithmic form or vice versa. And so the exponential form is 2 to the 4th equals 16. The equivalent logarithmic form will be whatever this exponent is, 4. It's equal to the logarithm of this number, that base. So the logarithm of 16 base 2 is equal to that exponent 4. And again, what the logarithm, if you were just given the log of 16 base 2 and you're asked to find out what number it equaled, that it equals 4, well, it's the 4 because it's 4 is the power of 2 that equals 16. 2 raised to that power equals 16. In the second one, we're given the logarithmic form and asked to write the exponential form. So converting, we will go this base raised to that power is equal to the 25. So 5 squared equals 25 is the equivalent exponential form. If we have in general a to the c equals b, remember if you're converting to log form, the exponent, the c, is what is equal to the logarithm. So the logarithm would be c equals the logarithm of b base a. Again, the base of the power is the same as the base of the logarithm. Flipping over to the second page, in this example we're going to evaluate a number of logarithms, and the first one is the logarithm of 8 base 2. Well, what logarithm means is whatever this equals is the power of 2 that gives you 8. So 2 to what power gives you 8? And that's equal to 3 because 2 raised to the power of 3 is equal to 8. So evaluating logarithms like this, it's helpful to know powers of 2 or 3 or 5 or whatever, and you can evaluate these quite quickly. For b, the logarithm of 1 base 4, that is equal to 0 because 4 raised to the power of 0 is equal to that 1. For c here, we're asked to evaluate the logarithm base 5 of 5 squared. Now 5 squared is equal to 25, so the question here is now, what power do we raise 5 to get this 25? And of course that's equal to 2, because 5 squared equals 25. This actually demonstrates a rule of logarithms that you might study in your course, and that's if these two bases are the same. If the base of the power and the base of the logarithm are the same, this actually equals that exponent. More generally stated, if you have the logarithm base a of a raised to the power of x. As long as the base of the logarithm and the base of the power are the same, that equals that exponent x. And that's an example of that in C. For D here, we're asked to evaluate the logarithm of a ninth base 3. So what we're really looking for, what power do we raise 3 to give you 1/9? And 3 raised to the power of -2. Remember, a negative exponent means the reciprocal then of the 3 squared, so it's 1 over 3 squared, or 1 over 9. So -2 is the power that you raise 3 to give you 1/9. So that is equal to -2. 3 raised to the power of -2 equals 1/9. In E here, we're asked to evaluate the logarithm of the root of 9 base 81. So we'll call it x until we actually find what x is. Rewriting this in the equivalent exponential form, we would have 81 raised to the power of x equals the root of 9. Now the root of 9 is 3. So 81 raised to the power of x equals 3. Well, if you're raising 81 to a power and getting a smaller number, then this x here is actually, you're taking some root of 81 to get 3. And now there's two ways I'm going to show you how to do this. It's the fourth root of 81 that gives you 3. So if you know your powers of 3 well, 3 to the power of 4 is 81. So the fourth root of 81 would be 3. That's one way you could do this. So the fourth root of 81 is 3, so x would have to be a quarter. Now, if that doesn't come to you very quickly, there's another way you could do this. You could look at this 81 to the power of x equals 3 and say, well, why don't we write the 81 and the 3 both as powers of the same base? And since this is 3 here, and I know that 81 is 3 to the 4th, okay, then you could try this. You could rewrite this as, okay, so the 81 is 3 to the 4th. So we've got 3 to the 4th, of course, raised to the power x equals 3. Now, when you have a power of a power, you multiply the exponent. So simplifying this, we get 3 to the 4x equals 3. Now, the 3 on the right is the same as 3 to the 1st. And if these two powers have the same base, then we can equate the exponents. The 4x should equal to 1. And so dividing out the 4, we get x is a quarter. So that's another way that you can get x as a quarter. Now the last one here, we're asked to evaluate the logarithm of 200. And a logarithm of 200 means the logarithm base 10 of 200. And so this is asking us what power of 10 gives us 200. That's what that logarithm means. And this is what these graphics are for down the bottom right hand corner. This is actually the graph of y equals 10 to the power of x. This line right here is y equals 200. So they intersect pretty closely at this point right here. At the bottom it's saying that the coordinates of that point are 2.3 comma, and it's not exactly 200, but it's very close, 199.52623, etc. So that means that in order to get a y value of about 200, x has to be about 2.3. This is the table here, and again it's showing that if x is 2.3, the y value for that function is 199.5, so very close to 200. So this is approximately 2.3. So once again, that means that if we raise 10 to the power of 2.3, it's approximately or very close to 200. So that's why the answer is 2.3 to that. Flipping over to the last page, on this page we're given the graph of y equals 2 to the power of x, and I'm going to graph a logarithmic function here to show what its general shape is. Now y equals 2 to the x and 2 to the y equals x have x and y switched, so these are actually inverses of one another. Now this logarithm, the y equals the logarithm of x base 2, this is actually the equivalent log form of this exponential form. Again, converting the exponent y would equal the logarithm base 2, again base of the exponential form, same as the base of the log form of x. Okay, so 2 to the y equals x. They are equivalent. Now, in order to show what this graph looks like, I'm going to illustrate several points in y equals 2 to the x. And we're going to put a couple of ordered pairs on here, a few of them. That's the point 0, 1, and that's actually 0, 1 because if I put 0 in here, 2 to the power 0 equals 1. This is the point 1, 2. If x is 1, 2 to the power 1 is equal to 2, so that's why the y value is 2 there. This is the point 2, 4, because if I put 2 in place of x, 2 squared equals 4. And then one more point, this is the point 3, 8. Because 2 cubed, if we put 3 in place of x, 2 cubed equals 8. So that's the point 3, 8. Now remember, to graph an inverse, one thing you can do is switch the x and y's and graph them, and then you get the graph of the inverse. So if I switch the point 0, 1, the x and y, I get 1, 0. So that's the point 1, 0. 1, 2 switch would be the 2, 1 point. So that's 2, 1. 2, 4, if we switch the 2 and the 4, we get 4, 2. So that's the point 4, 2. And then 3, 8 would become 8, 3 when we switch x and y. So that's the point 8, 3. And if we draw a smooth curve through them, that's what that inverse looks like. So that's actually the graph of y equals the logarithm of x base 2. Notice that it has the same shape as the exponential function, except they're reflections of each other in the y equals x line. So that's what the graph of a logarithmic function looks like.